All right. Okay. So looking at this slide here, what we see is the regression output. The first line is the call. That's what that's what you told R to return. It always returns the call. The second line are the residuals with quartiles, not that useful. I've honestly never used that for anything. I've never seen anyone use that for anything. We'll set that aside. If you continue along to 346, you'll most likely go into regression diagnostics and how to check if your model's assumptions are violated. That'll come into play a little bit more there. The big part we're going to focus on are the coefficients. The intercept is the predicted value of the outcome if all the independent variables are 0. Sometimes that's useful, sometimes it's not. In this case, this says that if you have someone who looks completely incompetent, then we'd expect them to lose by 38 percentage points. 38.4 percentage points. Is that number statistically significant? Is the intercept statistically significant? Yes. Its estimate is negative 38.4. The standard error is 8.7. So the estimate is negative 4.4 standard errors from 0. What that means is if someone looks completely incompetent, we would expect them to lose. And there's something systematic in the data that we can point at. Normally in the regression, as we move into more and more variables, the intercept itself is less interesting. It's the coefficients that are important. So we're going to start out with one coefficient today and then build up multiple coefficients. So for this coefficient, the competency measure is saying that if someone's competency goes from 0 to 1, we'd expect their electoral performance to improve by 77.6 percentage points. That's huge. Were I to read that in a JP or senior thesis or something like that, I'd minorly ding you on that sentence saying no one goes from looking completely incompetent to completely competent. So we've talked about this a few times. You want to change the 0 to 1 interpretation to a 1 percentage point increase because that's more natural, right? Go, if you're wearing a suit, go to a tailor, get a haircut, shave, that sort of thing. Like you can bump it up a little bit. Now, what's relatively new is looking at that second coefficient and saying, is it statistically significant? So let me go ahead and we'll flip to the next slide, which is going to go through the interpretation of the regression coefficient on that competency measure in a way that I'll be expecting of you, and in a way that you'll be doing whenever you run a regression analysis. So we're going to do this with one coefficient, then talk about what this means with multiple coefficients. So the coefficient itself is 77.465, which is the marginal effect of competency on votes, on vote share. So how do we interpret it? Well, a 1 percentage point increase in assessed competency leads to an expected increase of 0.77 percentage points in vote share. All right. So if anyone in this room is going to run for office, try to look competent. Okay. That's my practical advice for your life going forwards. So the next question is the effect substantively significant? In this course, I will ask you, is the effect substantively significant? And that's a matter of domain knowledge that in this course, I won't expect you to have, but I want to alert you to when you do your own future work. So is 0.77 percentage points in a race a big deal? Well, yes. In America today, yes, right? Like in this last election, Arizona, Pennsylvania, North Carolina, Georgia, how many races in the last 8 months were decided with less than 3/4 of a percentage point? Quite a few. Could it be the case that 0.77 is not substantively significant? Sure. You could say, everything's polarized and we're in a situation where we don't have close races. It turns out in America we do. but you could be talking about an electoral system where that's just not a big deal. When it comes to substantive significance, that involves background domain knowledge in what you're talking about. If you're ever doing a statistical analysis, spend time to know what you're talking about before you look at the data. Just speaking for myself, whenever I start a project that deals with something I don't know about, I'll read 3 to 5 books and 15 or 20 papers, which doesn't make me an expert, but it sort of makes me less likely to say horribly wrong things. And I'll always work with an expert, but it allows me to talk with them. In this case, for the purposes of this course, we are going to ask, is it substantively significant? Just follow that up with something intelligent. All right, we don't expect you to know what a reasonable compliance rate for COVID mask wearing is, or something like that, right? We're not public health experts, we're not epidemiologists. Just say yes and then something intelligent, or no and then something intelligent. But I want to get you in that habit of answering, does it seem substantively significant? So that when you go forwards and do your own analyses, you'll have that in your head at some point. The next question, so the course can't help with substantive significance. The course can help with statistical significance. So what we may want to know is that competency effect statistically significant? And that's where we start to talk about t-values and p-values. Is it statistically significant? Well, the t statistic is 4.649, which is greater than 2. Or you can say the p-value is 0.00001, which is less than 0.05. So if someone says, is it statistically significant? You can say yes, at the 95% level, it's statistically significant because the p-value is less than 0.05. You can also report the t statistic is 4.64, and people will know that means it's statistically significant. What does that mean? In this case, when we talk about the p-value, what we're saying in this case is that if we were to assume that the true marginal effect of competency in this model was 0, the probability of seeing an effect this large or larger is less than 0.00001. Okay? So if the data were generated such that the true coefficient was 0, the true parameter was 0, the probability of seeing the probability of seeing this effect or something larger in magnitude is really small, which simply means you're not likely to see this pattern in the data if there's actually no effect. And that's the logic we're trying to get at. For the purposes of the quiz, I do want you to be able to report back to me the probability of seeing a coefficient this large or larger in magnitude is less than 0.05, which is what statistical significance means. The last thing we might ask, or not might with a high probability, is to, like, what's the confidence interval? And to do that here, we can just take 77.465 plus or minus 1.96 times the standard error. And you can just read that off the regression table. Again, for the purposes of the quiz, you can just write out what I have on the left-hand side up there. You don't have to do all that multiplication. If you feel like it, you can truncate to the 10th, you can round to the 10th place and just do plus or minus 2 standard errors, but enough so that I know you're adding plus or minus 1.96 or 2 standard errors. Then you'll be asked, what does the confidence interval tell you? The confidence interval has the property that across repeated experiments, 95% of the reported confidence intervals will contain the true value. Does it tell us anything about this experiment? No, it doesn't. It just means this is pretty solid evidence that the effect is somewhere near 77.465. But we need to run a few more experiments to really get an idea of where we think it is. All right. Any questions? This is on the order of 4 to 6 questions on the next quiz, and I just wanted to give it to you so there are no surprises. Any questions on this before we roll ahead into a couple other things? Yeah.
It's like 95% of the studies in the true value in that range, right?
Oh, so the question is what exactly does coverage mean? right? So they ran an experiment and they got 77.465 plus or minus 33. Can I just say 33? So let's say they got 77 plus or minus 33, right? That we don't know if the true value is in there. If someone else comes along and redoes this experiment, which you can do, and they get 80 plus or minus 40, then someone else doesn't get 82 plus or minus 27, and you get all these different numbers. 95% of the confidence intervals, 95% of the experiments will lead to a confidence interval that contains the true value. It's not that 95% of, yes, 95% of experiments will generate a confidence interval that contains the true value. Does that make sense? Okay. Other questions on this before we move ahead? All right. Continuing along with just a single variable in a regression. There are two types of regressions you might encounter with a single variable. On one case, we might have the covariate xi be binary. In the other case, it is continuous. We've done both. Sometimes we put a treatment variable in for xi, sometimes we put a continuous variable. The confidence measure was continuous. Now, in the linear model, let's start with the binary side. On the left-hand side, in the linear model above, beta 0 is the expected outcome if xi is 0. Okay? And beta 1 is the difference in the outcome between xi equals 1 and xi equals 0. Why is that? When we change that 0 from xi to a 1, it bumps up, it puts a beta 1 in the outcome. All right? So in this case, our point estimates for the outcome given xi is 0 is just the estimated intercept beta hat 0. And the difference in means is beta hat 1. The estimated outcome if xi is equal to 1 is the estimated intercept plus the estimated beta hat 1. All right? Now what we're going to do is ask, well, how does that carry over? If xi is binary, we can use the regression for a difference in means. If xi is continuous, what can we do, right? There's nothing stopping us from putting a continuous variable in there. Beta 0 is the intercept of the line, and beta 1 is its slope. It's the average increase in the expected value of the outcome given a 1 unit shift in xi. It's a slope. If xi goes up 1, what do we predict is going to happen to yi? And we expect it to go up 1 in that. We expect it to go up beta 1 in that case. So a couple differences between the two different models. In the continuous case, we might be interested in the intercept, we might not. If you're trying to regress out someone's income on their height, we don't care about the intercept because we don't want to say things about people who are 0 centimeters tall, right? So if xi equals 0 is of interest, then we might look at the intercept. Normally, though, the intercept is just not all that interesting. We're more focused on the estimated slopes. What's the impact? What is the impact of a 1 unit shift in the xi on the predicted value of the outcome? That's what beta 1 is giving us. For a given xi, the fitted value is beta hat 0 plus beta hat 1 times xi. Now, with beta hat 1, whether it's a difference in means or a slope, we can construct a confidence interval on it by just doing beta hat 1 plus or minus 1.96 standard errors. Equivalently, we can construct a t-statistic, which is beta hat 1 over its standard error, and just see if it's bigger than 2 or in magnitude, and get a p-value from it. So the particular mode of inference we're conducting, whether constructing a confidence interval or a confidence interval or a p-value, doesn't really vary with whether xi is continuous or binary. What does vary is how we're interpreting the different parts of the model. Okay. We saw this slide before. I just want to run through it briefly. So the different elements of the regression table, the coefficients is the estimated effect of a 1 unit shift in the independent variable on the predicted value of the outcome. If I move xi, what happens to my fitted value? The standard error is our uncertainty estimate on the coefficient. Depending on the model, you'll next return a t-value or a t-value or a z-value, and that's the coefficient divided by the standard error. It's the answer to the question, how many standard errors is my estimate from 0? The p-value is the probability of observing a coefficient that large or larger in magnitude if the true effect were 0. N is the sample size, and R squared is the proportion of the variance in the observed data captured by the model itself. Okay. Next, we're going to start going into multiple variables. And here we're just going to look at 2 variables. The outcome is going to be GDP per capita. And then our independent variables, we're going to have 2 of them, is going to be ELF, which is a Will Ferrell movie where he was an elf that worked for Santa. But how did it go? He had to, why did he leave the North Pole? Because what? To find his dad. Thank you. Yeah. No, my wife does Christmas movies, not me. She started watching Hallmark Christmas movies like yesterday. Does anyone else do that? Okay, some of you. Good. Actually, no. ELF is not the Will Ferrell Christmas vehicle. It is a standard measure in comparative politics called ethno-linguistic fractionalization. There's a few different ways to conceptualize it, but perhaps the simplest is if you have a population of people, if you choose 2 people at random, the probability that they speak the same language is the measure of ELF. And there's more mathematical ways to derive it, but that's kind of what it boils down to. So that's ethno-linguistic fractionalization. And then oil production. Why might we do this as social scientists? Well, we might be interested in GDP per capita. And we might want to know what's the relationship between ethno-linguistic fractionalization and GDP per capita. Because off the top of my head, my supposition would be the more fractionalization in your society, the lower growth, simply because it's harder to trade and communicate, right? And then the second one might be, well, the more oil, the more GDP per capita you might expect. And those are just my both off the top of my head. There's entire literatures on both of these. Okay. So let's look at these results where we regress log GDP per capita on ELF and oil production. So what this is telling us is, let's go through these one at a time. The intercept, is the intercept interesting? Perhaps. If there's a country that has no ethno-linguistic fractionalization, so it's just perfectly homogeneous and everybody speaks the same language and everybody's the same ethnicity. I can't think of a country like that, but at least it's an interesting hypothetical. What's that? Is Mongolia one? Okay, so that's talking about Mongolia. In that case, if ethno-linguistic fractionalization was 0 and they don't produce any oil, then we expect their GDP per capita to be 24.88. Okay. Now what we might want to know, it could be the case in this case, the intercept is perhaps interesting depending on how interested you are in Mongolia. But I'm not being there. No. There's people study things. But if you're not, and you're just trying to make a broad statement about all the different countries, the intercept is not normally of interest. So we're going to leave the intercept out for now. What we're more interested in is if we were to imagine a country and we were to fix the amount of oil that it had and increase its ethno-linguistic fractionalization, what would that do to the predicted value of GDP per capita? Notice, and I'm trying to be careful with this, none of this is causal language. right? Nothing here is randomized. We can't randomize linguistic fractionalization. We can't randomize oil production. All of these are descriptive. But if we were to imagine two countries with the same amount of oil, but one had a higher level of ethno-linguistic fractionalization, what would that do to growth, GDP per capita? The answer is that coefficient, negative 0.023370. So that negative 0.02 coefficient. That says if ethno-linguistic fractionalization were to increase by 1, GDP per capita logged, we'd expect it to go down 0.02. Okay, so we fix the amount of oil and we drop GDP per capita. Sorry, we increase ethno-linguistic fractionalization by 1, we'd expect GDP to go down. Log GDP per capita to go down by 0.02337. Okay, the next question we might have is that relationship statistically significant? Here we have to see how precisely we measured it. The standard error on that coefficient is 0.001. Its t-value is negative 14. So the p-value is clearly going to be less than 0.05. And you can see that in the last column where the p-value is less than 2e negative 16. That just means it's less than 15 zeros than a 2. 0.15 zeros than a 2. One thing I want to highlight, you don't get extra credit for having that sort of significance. Something is statistically significant or not. A number is below 0.05 or not. Okay, you don't have any extra oomph just because of that. All we can say is it's statistically significant. Now we might want to come along and say, you know what? What happens as oil increase? What happens to our predicted values if oil goes up? And in that case, a 1 unit increase in oil decreases GDP per capita by negative 0.003. But now we ask, is the effect statistically significant? So what we're imagining is a country with a certain level of ethno-linguistic fractionalization, and then 2 countries with oil that differ by 1. And then what does that do? Well, that leads our predicted value of GDP per capita logged to go down negative 0.003. Is that statistically significant? Well, first we have to turn to the standard error and see how precisely our 0.003 was estimated. The standard error is 0.004. What that means is that our t-value is negative 0.6667, which is the negative 0.003064 over 0.004527. So is there a statistic, and the p-value is 0.499. So we found a statistically significant relationship between ethno-linguistic fractionalization and growth, GDP per capita, but we did not find one for oil. This is a monstrously naive regression if anyone studies growth economics. I just want to make that completely clear. I'm making no claims about what actually drives growth. This is to illustrate a regression with 2 variables, one of which is significant and the second one is not statistically significant. So how would we interpret this? We find, after adjusting for oil, we find a statistically significant relationship between ethno-linguistic fractionalization and GDP per capita logged. But after adjusting for ELF, which means holding linguistic fractionalization fixed, we don't find a statistically significant relationship between oil levels and GDP per capita. Right? And that's how we interpret this sort of regression. So what we're doing is we're saying for one coefficient at a time, if I fix all the other coefficients and fix all the other variables, what's the impact of a 1 unit move in the variable I'm looking at on the outcome? All right. Now we're going to return to an important part and possibly one of the most important parts of a regression model. It only gives decent results if your model's correct. And we're going to talk about the primary mechanism by which it does so, by which you might get incorrect answers. And that's referred to as omitted variable bias. It's a bias because it biases the results, and it's caused by a variable that you don't put in that you should. So we're going to return to Abanya Washington's data. Recall in this data, the outcome was an index on the scale of 0 to 100 on a candidate's score, how a candidate was scored by the National Organization of Women. Abanya Washington interpreted that as pro-feminist views. We can have that argument in a different course at a different time. I'm not even sure it's right or wrong, but like, please do think you should push against that. It might be right to you, it might be wrong. What we want to know is, how does the number of daughters that a legislator has impact their score by the National Organization of Women? And that was Abanya Washington's question. Because in this country, by and large, the number of children, the gender makeup of your children is random. It's either completely random or somewhat random. I had one friend who kept on having children till he got a girl, right? But like there's those, but like outside of those sorts of cases, it's by and large random. So what we're going to do is, first we're going to regress the now score on just the number of girls, N girls, which is the number of daughters that someone has. And what you'll see is a negative relationship, negative 2.15, but it's not statistically significant. Why? Because it's negative 2.15, but the standard error is 1.56, and the coefficient is not two standard errors from 0. All right, 1.56 times 2 is 3.12, which is larger than the coefficient. So in the original data, what you'll see, if you just regress one on the other, is if anything, having more girls it has no real relationship on how someone votes, which I'd buy, maybe, right? That doesn't seem wildly implausible. But the effect, if there is one, seems to be that having more girls makes you less supportive of the agenda of the National Organization of Women. Okay. What's driving this result? Well, we don't include all the variables we should have in there. There are other variables that predict voting patterns and predict how many daughters someone has that we need to include as control variables, and we need to put all of them in. Okay? So the first one we're going to talk about, and this came up, I think, in one of your precepts, we might want to adjust for family size, right? How many children do you have in total? Because there's two ways to get one more girl. One is to have a larger family. One is to have had a girl instead of a boy. Those are different dynamics and different causal mechanisms. Larger families are associated with social conservatism in this country, and we can see that happening here. In this case, if we fix the number of girls, let's look at the second model. If we fix the number of daughters that a legislator has and increase the family size, it leads to a 7-point decrease in their score by the National Organization of Women. Again, consistent with the social conservatism story. Now let's look at the number of girls coefficient. This says if we were to fix the total number of children, but swap out a girl for a boy for a girl, their score for the National Organization of Women would go up by 5 percentage points, 5.45. Now we're starting to see a more subtle and I think believable story emerging from the data. Omitted variable bias is how that -2 went to 5.45. From column model 1 to model 2, the omitted variable was total number of children. Putting it in there changed our estimate and it debiased the estimate. So now it's at 5.45 instead of -2. The last few things to talk about, and she includes a whole host of other control variables, but let's go through some of the more obvious ones. What else predicts voting behavior in the US Congress? Well, this is Congress, right? Like it's the US Congress. Party matters, okay? So in that case, she included a dummy variable for Republican. So what that's saying, in reading down the line here, is if we were to, let's look at the number of girls. If we were to fix the total number of children that someone has and fix their party, then going from one boy to one girl increases their support for now by 3.24. Is that 3.24 statistically significant? Yes, the standard error is 1.21. So the coefficient is more than 2 standard errors from 0. Helpfully, the asterisk after the coefficient conveys that information. All right. Looking around at the other variables, well, if we freeze the number of daughters someone has and we freeze their party, but then we ask, as the total number of children goes up, so if we give them one more child, what happens to their support for now? And it goes down by 3 percentage points, but if the score goes down by 3, is it statistically significant? Yes, the asterisk helps, but also the fact that the standard error is clearly, it's more than 2 standard errors from 0. Twice the standard error is less than the coefficient in magnitude. Last one, which variable is doing most of the work? Well, party. Again, it's Congress, right? Republicans, other things equal, according to model 3, the Republicans support the National Organization of Women by about 60 points lower than Democrats. Does that more or less make sense to folks? Yeah, that shocks nobody, I hope, who follow these issues. So we're going to put in the Republican variable because it's Congress. What other variables might we include? Well, we can include whether or not the legislator's female. Oh, there's an interesting point about the Republican variable, by the way. You can't put in a Democratic variable because Bernie Sanders was in the state in the US House and he was an independent socialist or something, or an independent knitter. Or was he sitting with was he knitting when he had those gloves on, or was he was just sitting there? Okay. Anyways, you need to put in a Republican variable because if you put in a Democratic indicator variable, it puts Bernie with the Republicans, which makes him cranky. So there's a Republican variable in there. Now you're saying, well, we're talking about issues of gender and representation very, very roughly, but still it's what we're talking about. It could be that female legislators, all else equal, vote differently regarding the National Organization of Women relative to men, right? That's not a crazy thought. There was a recent paper in one of our journals that actually found that countries with larger numbers of women in their parliament were likely to have lower taxes and lower tariffs on consumer goods that were more likely to be used by women. It was called a pink tax if you want to look up the paper. But there's some evidence that this gender representation, just strictly gender alone, matters. So let's look at the fourth model, which is the one we're going to settle on for now, which has an intercept. And so the impact of fixing someone's total number of children, their party, and their gender, but putting one more person and one more daughter in their family is 2.88 with a standard error of 1.18. Is that statistically significant? Yep. The asterisk tells us, and the fact that it's more than 2 standard errors from 0 tells us. Having total number of children, also a one child increase, but fixing the number of sons and daughters and fixing their party and their gender, a 1 unit increase in total number of children leads to a decrease of about 3% of 3 points on Now's score. It's also statistically significant. Party is actually doing most of the work on predicting the vote. So in this case, the effect is 60 percentage points, or 60 points for now. But it's also, I thought, interesting that on average, females, other things equal, fixing the number of fixing their party and family size and number of daughters, whether someone's female is also statistically significantly associated with voting for now at a higher level. And that's what that last column is telling us. The takeaway from this discussion is that if you want to interpret, in this case, the variable n girls, you need to include other variables in the multivariate regression that you're adjusting for or that you're fixing. Sometimes it's called controlling for. You want to include all of the basic variables that predict both the outcome and the variable you're interested in. So what are the big predictors of how someone votes for now? Well, in Congress, it's clearly your party. It might be whether you're female, it might be family size. What are the major predictors of how many daughters you have? Well, how many children you have, right? So we want to include that in. And that's where this control set came in. What other, this was not the regression that she published in the paper, it was close to it. But what other control variables might you want to include in here to help eliminate anything that might be biasing the effect of N girls, which was the variable she theorized? Yeah.
I have a quick question.
Please.
Are we like
So we want to control for two things. Confounders, which are things that can affect the treatment and the outcome, but also just anything that could affect the outcome that might also affect the treatment. So anything that could predict the outcome, in this case, it's party. You want to take the variables that that adjust for the outcome. You want to find variables that predict the outcome and variables that predict the treatment. And you want to put them together and include those as a control set. If you refer to them as confounders, that's totally acceptable. Did that answer the question?
okay?
So the thought process for this model is what might drive how many daughters someone has, and you list some things out. Okay, then you ask yourself, well, what might drive how someone votes for the National Organization of Women, and you list some things out, and you take those two groups and put them together, and that becomes your control set. All right, did that address the question? Okay. So what other variables? Yeah. Yep, so perhaps what region you come from, right in the US, whether you're from the South or the Mountain West or the Sun Belt or the West Coast or the East Coast or the upper, Midwest, like that can have an impact. What else? Yeah. Mm-hmm. She doesn't include the region, though she could or should have. She does include religious affiliation. If you go back and look at the original paper, there's variables for, there's doctrinal differences on how many children you should have between Catholics, and she includes Buddhist, Jew, like all the different categories that are used in the data. So religious affiliation, you had one? Religious affiliation, okay. Any others? Yeah. Income. How wealthy is someone, right? Like how much do they actually need these, I don't want to go down a political rabbit hole, but a lot of these gender issues and issues that regard women fall hardest on low income women. Other thoughts? Yeah. Age. That could be a combination of both generational. When did someone come of age? Because like you guys have different gender conceptions than me, than I have of my parent, my parent, like that's I think supposed to happen, or I hope it is. But age, or it could just be like as you get older, you get more loving or crotchety, or I don't know. I'll find out. Any other variables? Okay. So the work of a model is collecting and measuring all those variables and then putting them in the regression. You'll also want to make sure when you include them that the variables go in the expected direction, which means for a lot of these variables, we know that the Republican variables should have been negative. And it's just a good model check that all the coefficients are in the direction that you think it should be, given the world we live in. The next one we're going to take a look at is from the Journal of Politics in 2007. The outcome is the change in George W. Bush's vote share in a state from 2000 to 2004. And what the author wanted to know is, was there a statistically significant relationship between number of fatalities in Iraq from a given state and support for the president? I think there's at least a fairly clear story behind that. If the president initiates a war like he did in Iraq, and the casualty incidents vary state by state, in states with the highest levels of per capita incidents, did he suffer at the ballot box? Supposed to at least see the argument in there? Let's see what the author had. So in this case, the average number of casualties over the country per 100,000 was 3.39. So the total Iraq deaths and wounded per 100,000 was negative 0.0055 with a 0.0023 standard error. Is that statistically significant? Well, what's two standard errors in this case? 0.0046, the coefficient is larger than that in magnitude. So in fact, the author found a statistically significant effect. He found that, other things equal, the total Iraq deaths and wounded per 100,000 predicted lower support for George W. Bush in 2004 relative to 2000. Okay, so the question is, what else did he control for in this regression? Well, the proportion active in armed forces in 2000, the proportion veterans in 2000, which might be driving enlistment, the change in unemployment because the economy kind of affects everything, the change in the Black population proportional 2000 to 2003, because we're talking about support for George W. for any presidential candidate in the United States, the change in the white population in each state, because all of those have an effect on turnout and vote outcomes, and the proportional change in total population. So that's what he adjusted for. It's 2:20. I will see you all on Thursday.